We're back on the ocean floor. Last time, we were here roughly 570 million years ago, surrounded by the Ediacaran biota. Soft, flat, motionless things. Organisms that absorbed nutrients through their skin and stood in the dark like quilted flags. A silent world. A gentle world. That world is gone now. It's roughly 520 million years ago, give or take, and the ocean floor looks completely different. The first thing you notice is the sediment. It's churned, mixed, disturbed. The thick, smooth bacterial mats that covered everything in the Ediacaran, the mats that entire ecosystems depended on, are broken up, riddled with holes and tunnels. Something has been digging. The second thing you notice, fragments. Tiny, hard, sharp fragments scattered across the seafloor. Shells, spines, scales, little pieces of armor. Some the size of a grain of rice, some the size of a fingernail. This is called the small shelly fauna. And it's the first sign that something fundamental has changed. Because here's the question. Why would any organism evolve armor? Armor is expensive. It takes energy to build. It takes calcium or chitin, which are metabolically costly. It makes you heavier. It makes you slower. No organism evolves a shell for fun. You evolve a shell because something is trying to eat you. And if things are growing armor, if the ocean floor is suddenly littered with tiny shields and spines and plates, that means something is out there, hunting, attacking, killing. For the first time in 4 billion years of life on Earth, something is eating something else, on purpose. This is the Cambrian explosion, and it is, without exaggeration, the single most important event in the history of animal life. This is when nature invented war. The Cambrian explosion is one of those terms that sounds dramatic, because it is dramatic. Starting roughly 540 million years ago and lasting approximately 20 to 25 million years, the Cambrian explosion produced, as far as we can tell, every major animal body plan that exists today. Arthropods, insects, spiders, crustaceans appear in the Cambrian. Mollusks, snails, clams, cephalopods appear in the Cambrian. Chordates, the group that includes every animal with a spine, including you, appear in the Cambrian. Echinoderms, starfish, sea urchins, Cambrian. Annelids, earthworms, leeches, Cambrian. Every door, every branch, every fundamental body plan in the animal kingdom, all of them trace back to this one window of time. And here's the staggering part. In the 500 million years since the Cambrian, 500 million years of evolution, of mass extinctions, of continents splitting and oceans forming and life adapting to every conceivable environment, not a single new animal phylum has appeared. Not one. Everything since, every dinosaur, every shark, every whale, every eagle, every human, is a variation on a Cambrian theme. The blueprints were drawn in those 20 million years. Everything else has been renovation. We know this in extraordinary detail because of one place. In 1909, a paleontologist named Charles Doolittle Walcott was riding his horse along a mountain trail in the Canadian Rockies in what is now Yoho National Park, British Columbia. His horse stumbled on a piece of shale. Walcott dismounted to look at it. Inside the rock, preserved in exquisite detail, were the remains of soft-bodied marine animals, not just shells and bones, soft tissue, legs, guts, eyes, antennae, feeding appendages, all perfectly flattened and preserved in 508 million-year-old mudstone, the Burgess Shale. Over the following years, Walcott extracted over 65,000 specimens from that single rock outcrop. It remains one of the most important fossil sites in the history of science, a snapshot of the Cambrian Ocean, preserved in almost photographic detail. and the animals inside it were unlike anything anyone had ever seen. If you had to name the single most important invention of the Cambrian explosion, the one thing that changed everything more than anything else, it wouldn't be teeth, it wouldn't be shells, it wouldn't be claws, it would be eyes. Before the Cambrian, no organism on Earth had image-forming vision. Some bacteria could detect light. Some ediacaran organisms may have had light-sensitive patches. But seeing, forming an image of the world, detecting shapes, tracking movement, identifying predators and prey at a distance, that didn't exist. The world was blind. And in a blind world, there's no real advantage to being fast. There's no advantage to being camouflaged. There's no advantage to having armor, because nothing can see you to target you. Then eyes appeared, and everything changed overnight, geologically speaking. This is the light switch hypothesis, proposed by biologist Andrew Parker in 2003. The idea is elegant and terrifying. The moment one lineage of animals evolved functional eyes, it created an arms race that cascaded through the entire ecosystem. If a predator can see you, you need to hide. If you hide, the predator needs better eyes. If the predator has better eyes, you need armor. If you have armor, the predator needs stronger jaws. If the predator has stronger jaws, you need spines, speed, burrowing ability, chemical defenses. One innovation, vision, triggered a chain reaction that produced every defensive and offensive adaptation in the animal kingdom. In 20 million years, the trilobites were among the first. We met them in the Ordovician, hundreds of millions of years later. But they were already here in the Cambrian, and their eyes were already extraordinary. Compound eyes made of calcite crystal, the same mineral lenses we discussed in the first video. Hundreds of individual lenses per eye, arranged in precise geometric grids. Some Cambrian trilobites had eyes that wrapped nearly 360 degrees around their heads, panoramic vision, with almost no blind spots. These were prey animals, and they needed to see in every direction, because something was hunting them. But the best eyes in the Cambrian didn't belong to the trilobites. They belonged to the hunter. Each of its eyes contained approximately 16,000 individual lenses. For comparison, a modern housefly has about 4,000. A dragonfly, one of the best-sighted insects alive today, has about 28,000. This animal had dragonfly-level vision, 500 million years ago, in an ocean where most things could barely see at all. Those eyes belong to Anomalocaris, and we'll get to it. But first, the weird stuff. The Burgess Shale didn't just preserve the ancestors of modern animals. It preserved things that don't seem to be the ancestors of anything. Evolutionary experiments, dead ends, designs so strange that when scientists first reconstructed them, they got them completely wrong. Hallucigenia. In 1977, paleontologist Simon Conway Morris published the first reconstruction of a tiny Burgess Shale animal he named Hallucigenia sparsa because, he said, it looked like something from a hallucination. His reconstruction showed a worm-like body walking on 7 pairs of rigid spines, like stilts, with a row of floppy tentacles waving along its back. One end had a round blob that he interpreted as the head. It looked absurd, like a creature designed by a committee of people who had never seen an animal before. That's because Conway Morris had it upside down. In the 1990s, new specimens and new analysis revealed the truth. The stilts were actually dorsal spines, defensive structures pointing up from the animal's back. The tentacles were actually legs, soft, stubby, walking limbs on the underside. And the head, that was the rear end. The actual head was at the other end, thinner, smaller, with a tiny mouth. For nearly 20 years, every textbook, every museum, every illustration of hallucigenia was upside down and backwards. The corrected version is still strange. A worm-like body about 3 centimeters long, with 7 pairs of walking legs, 7 pairs of dorsal spines, and a head with a simple ring of teeth around the mouth. Modern analysis places it as a relative of velvet worms, Onychophora, soft-bodied creatures that still exist in tropical forests today. But if you saw it alive, you would not think worm. You would think nightmare. Whittington, about 5 centimeters long, oval-shaped, crawling along the sea floor. Its upper surface was covered in rows of overlapping scales, like a pangolin or a pine cone. And from the middle of its back, 2 rows of long, blade-like spines extended upward, sharp, flat, and clearly defensive. A scaly, bladed oval. Not a mollusk, not a worm, not an arthropod. What is it? The honest answer, we're still arguing. Some paleontologists place it close to mollusks. Its scales resemble the sclerites found on some primitive mollusks. Others see similarities to polychaete worms. The current best guess is that it sits somewhere near the common ancestor of mollusks and annelids, before those two groups fully diverged. Whittington might be a glimpse of what life looked like before the familiar categories solidified, before mollusk and worm became separate things. A creature from the moment when the tree of life was still deciding which way to branch. Opabinia. 5 eyes. 5. 2 on the front of the head, looking forward. 2 on the sides, looking laterally. 1 on top, looking up. And extending from the front of the head, a long, flexible, segmented proboscis, roughly a third of the body length, ending in a small, claw-like grasper. The proboscis curved downward and backward, toward the mouth, which was located on the underside of the head, facing backward. To eat, Opabinia would grab food with the tip of its proboscis and pass it backward, underneath its own head, into its mouth. Like eating by reaching over your head with a grabbing tool and stuffing food into a mouth on the back of your neck. When Harry Whittington, one of the paleontologists who restudied the Burgess Shale in the 1970s, first presented his reconstruction of Opabinia at the annual meeting of the Paleontological Association in 1975, the audience laughed, not politely, not with gentle amusement. They laughed because they thought it was a joke. They thought Whittington was testing them, presenting a deliberately absurd reconstruction to see if anyone would call it out. He wasn't joking. Opabinia was real. Every detail of it was real, and it still can't be confidently placed in any known animal group. It's not an arthropod, though it has some arthropod-like features. It's not an annelid. It's not a mollusk. Like hallucigenia and Whittington, it seems to belong to a period of evolutionary experimentation when the boundaries between animal groups hadn't yet hardened. 5 eyes, a backward-facing mouth, a grasping proboscis, 7 centimeters of pure evolutionary chaos. And it wasn't even the most dangerous thing in the water. Anomalocaris was discovered in pieces, and the pieces fooled everyone. In 1886, a strange fossil was found in the Canadian Rockies. It looked like the body of a shrimp, but wrong somehow. Curved, segmented, with spines along one edge. It was described as a new species of crustacean and named Anomalocaris, anomalous shrimp. Separately, in different rocks, a circular fossil was found, a ring of hard plates arranged like a pineapple slice, with a central opening. It was classified as a jellyfish, and in yet another specimen, a long, flat body with lateral lobes was found and described as a sea cucumber. 3 fossils, 3 different species, 3 different phyla. Shrimp, jellyfish, sea cucumber. They were all the same animal. In 1985, Harry Whittington and Derek Briggs, the same team that had deciphered Opabinia, were re-examining Burgess Shale specimens when Briggs found a complete Anomalocaris, one specimen with everything connected. The shrimp was a frontal appendage, a grasping arm. The jellyfish was the mouth. The sea cucumber was the body. One animal, assembled from parts that 3 generations of scientists had been looking at separately for nearly a century, and when they put it together, they realized what they had: Anomalocaris canadensis, up to 1 meter long, possibly longer. In an ocean where almost everything else measured between 1 and 10 centimeters, this was a giant, the largest animal on the planet, by a factor of 10. The frontal appendages were spectacular. 2 large, flexible arms extending from the front of the head, each lined with a row of inward curving spines, like the tines of a comb, but sharp and attached to a limb that could curl inward like a fist closing. They were grasping tools, designed to seize prey, hold it, and bring it to the mouth. The mouth itself was a circle of 32 overlapping plates, arranged in a ring, contracting like the iris of a camera. Studies show it couldn't close completely. There was always a small gap in the center. But the plates could exert crushing force on anything trapped between them. We know this because we have the evidence. Fossilized trilobites from the Cambrian, multiple specimens, show distinctive W-shaped bite marks along their edges. The size, shape, and spacing of these marks match the oral plates of Anomalocaris exactly. Some trilobites show healed bite marks, meaning they survived the attack but carried the scars. Others show fatal damage, crushed exoskeletons, missing segments. Anomalocaris was actively hunting trilobites, grabbing them with its appendages, bringing them to its circular mouth, and crushing their armor. And those eyes, compound eyes on short stalks, each containing approximately 16,000 individual lenses. These were not simple light detectors. These were precision optical instruments, capable of forming sharp images, detecting movement, and estimating distance. For context, a modern ant has about 100 lenses per eye. A housefly has about 4,000. A dragonfly, widely considered to have the best compound eyes of any living insect, has about 28,000. Anomalocaris had 16,000 per eye, 500 million years ago, in the first generation of predators the world had ever seen. This was not a primitive animal fumbling in the dark. This was a precision hunter, the first apex predator in Earth's history, with better eyesight than most insects alive today. It swam using undulating lateral lobes, rows of flexible flaps along each side of its body, rippling in sequence like a manta ray's wings. Not the fastest swimmer, but maneuverable, and in an ocean where most prey could barely crawl, it didn't need to be fast. It just needed to see you, and it could. From further away, in greater detail, and with better clarity than anything else alive on the planet. The first apex predator. The first thing with eyes good enough to find you, arms strong enough to hold you, and a mouth built to break you open. Nature's first nightmare. And everything after it, every shark, every tyrannosaur, every killer whale, is a descendant of the world that Anomalocaris created. Because once one animal evolved the ability to hunt, everything else had to evolve the ability to survive. And that arms race, predator versus prey, attack versus defense, speed versus armor, has never stopped. It's been running for 500 million years. And it started here, with a meter-long shrimp that scientists couldn't even recognize as a single animal. Now, somewhere in this chaos, in this ocean of armored predators and spined prey and five-eyed hallucinations, there was one organism that nobody would have noticed. Pichia gracilens, about 5 centimeters long, flat, ribbon-shaped, vaguely eel-like. It swam in the water column with a series of S-shaped undulations, the same basic movement a modern eel or fish uses. No armor, no spines, no claws, no exceptional eyes, nothing to suggest it was anything special, except one thing. Running along its back, a thin, flexible rod, a notochord, the precursor to a spine. Pikaia is one of the earliest known chordates, a member of the phylum that includes every vertebrate on Earth, every fish, every amphibian, every reptile, every bird, every mammal, every human. This 5-centimeter worm, defenseless, unremarkable, swimming through a Cambrian ocean, filled with things that could eat it without slowing down, is near the base of your family tree. It had no idea what it would become. In 500 million years, its descendants would grow jaws, teeth, bones, and brains. They'd leave the water, walk on land, build cities, split atoms, send robots to Mars. But here, in the Cambrian, it was nothing. A footnote. Prey. Something Anomalocaris might have eaten as a snack between trilobites. There's something almost unbearable about that. The absolute randomness of it. The fact that everything you are, everything every human has ever been or will be, traces back to a 5-centimeter worm that happened, by pure chance, to not get eaten on any given day in a 520-million-year-old ocean. If Anomalocaris had been slightly faster that day, if the water had been slightly clearer, if Pikaia had zigged instead of zagged, different story, different world, no one to tell it. So why did all of this happen at once? 20 million years, every major animal body plan, an explosion of complexity that the planet hadn't seen in 4 billion years and hasn't repeated since. Why here? Why now? Why all at once? The honest answer is, we don't fully know, but we have 3 hypotheses that, together, probably cover most of the truth. Hypothesis 1, the light switch, Andrew Parker's idea, published in 2003. The evolution of image-forming eyes, possibly in an early arthropod ancestor, triggered a cascading arms race. Before eyes, predation was random. A blind predator might stumble into prey. A blind prey might stumble into a predator. Neither could target the other. The selection pressure for speed, armor, and camouflage was low. After eyes, suddenly predators could choose targets. They could pursue. They could select the weakest, the slowest, the least armored. And prey, for the first time, could see death coming. That single change, the ability to see, turned a passive, slow-motion world into an active, high-speed arms race. Every adaptation we associate with animal life, armor, speed, camouflage, venom, burrowing, schooling, mimicry, can be traced back to the selection pressures created by vision. One sense, one change, everything else followed. Hypothesis 2, oxygen. By the beginning of the Cambrian, atmospheric oxygen levels had risen to a critical threshold, possibly around 15 to 20% of modern levels, up from near zero for most of Earth's history. Oxygen matters because muscles need it. Active predation, chasing, grabbing, crushing, requires an enormous metabolic output. You can't sustain that on anaerobic metabolism. You need oxygen, lots of it. When oxygen crossed the threshold, active lifestyles became possible for the first time. Animals could move fast, sustain effort, grow larger, support complex tissues, eyes, brains, muscles. The ediacaran organisms didn't need much oxygen. They sat still and absorbed. The Cambrian animals were running, swimming, chasing, and fighting. That requires fuel, and the fuel had finally arrived. Hypothesis 3, the genetic toolkit. This one is the most counterintuitive. The genes responsible for building complex body plans, Hox genes, The master switches that determine where heads grow, where limbs form, where eyes develop, may have been in place long before the Cambrian. In other words, the instructions for building complex animals already existed in the DNA. What didn't exist were the conditions that made complex bodies useful. When oxygen rose, and eyes appeared, and the arms race began, those pre-existing genetic programs were activated, rapidly, across multiple lineages, simultaneously. The Cambrian explosion wasn't evolution suddenly speeding up. It was evolution deploying tools it had been building for hundreds of millions of years, all at once, because for the first time there was a reason to. 3 causes, 3 triggers, 1 result, the birth of the animal kingdom as we know it, in 20 million years, on the floor of one ocean. 500 million years ago, give or take, on the floor of an ancient ocean, nature wrote the rules of animal life: eyes, teeth, armor, speed, predation, defense, fear. In roughly 20 million years, a geological heartbeat, every major body plan in the animal kingdom appeared. Arthropods, chordates, mollusks, echinoderms, annelids, all of them, at once. And in the 500 million years since, through 5 mass extinctions, through the age of fish, the age of reptiles, the age of mammals, the age of humans, not one new phylum has been added, not one. Every animal you have ever seen, every pet, every pest, every predator, every creature in every documentary, is a variation on a Cambrian theme, a remix, an upgrade, never a new invention. The blueprints were drawn here, by blind luck, chemical accidents, and a meter-long predator with 16,000 lenses in each eye. And everything we think we know about what these animals looked like, the reconstructions in textbooks, the models in museums, the CGI in documentaries, is built on guesswork, educated guesswork, brilliant guesswork, but guesswork nonetheless. Because here's the dirty secret of paleontology that nobody likes to talk about. Almost every prehistoric reconstruction you've ever seen is, to some degree, wrong. The colors are wrong. The textures are wrong. The behaviors are wrong. The soft tissues, lips, skin, fat, feathers, are almost always wrong. And we know this because every decade or so, a new discovery comes along and proves that the previous version was built on assumptions, not evidence. How wrong are they? How do we know? And what should these animals actually have looked like? That's next time. Until next time, stay curious, stay terrified,